Hi everybody. Today I will discuss about periodic functions and Fourier series. A function fx is said to be periodic if the value of each ordinate, fx, repeat itself at equal intervals in the abscissa. This point we will check in the graph for y equal to sine x and for all values of x. We can write function of x equal to function of x plus t equal to function of x plus 2t. Here difference between these two terms, it is t. Again difference between these two terms, it is also t. If there would be another term here, difference between these two also would be t. So what you can say, t is the interval between two successive repetitions and it is called the period of the function fx. So let's move ahead to see details of it to understand. Here y equal to sine x, it is periodic function in x. And this periodic function, it can be written as this: sine x equal to sine x plus 2 pi equal to sine x plus 4 pi and so on. So what's the difference between these two? 2 pi. Again, difference between these two also 2 pi. If there would be another term, difference between these two would also be 2 pi. 2 pi, it is period. And from here to here, up to this 2 pi, we call it as one wavelength. In bracket I have written periods. As I said, ordinate function of x repeat itself. This one, it is amplitude. This ordinate is amplitude. It is repeating here also. That's why from here to here we call it as one wavelength, because repeat starts from here for the next wavelength. And the range of x, it is less than equal to 2 pi, greater than equal to 0. I mean from here to here. Amplitude is 1. That is why my equation is y equal to sine x. 1 is here. If amplitude would be 2, then it will be 2 sine x. Then this crest, this point, it would rise here at 2. This also would rise here. This also would go here. In that case, amplitude 2. So equation would be y equal to 2 sine x. But here we have y equal to sine x, this one. And this is the standard curve. Here we have taken y equal to cos x. It is periodic function in x, and equation we can write as this: cos x equal to cos x plus 2 pi equal to cos x plus 4 pi, and so on. So difference 2 pi. Here difference 2 pi. That's why we can see here 2 pi. So from here it starts, and this point again it repeats from here. That is why from here to here we call 2 pi. It is one wavelength. T equal to 2 pi. Same way we can write x less than 2 pi greater than equal to 0. From here to here. Amplitude is 1. Here it is 1 amplitude. Here also amplitude 1. That's why equation is y equal to 1 into cos x. Already I explained, if it would be 2, then this crest would be here, this would be here, and in that time equation would be y equal to 2 cos x. So difference between these two, it is the periods. And already I have written y equal to cos x. This is the curve for the y equal to cos x. It is periodic functions. Now important points we have about Fourier series. But we will use this concept of periodic function to understand Fourier series. Let's move ahead to see. Suppose we have a periodic functions, and under certain condition it can be expressed as the sum of an infinite number of sine function or cos function. Sum of an infinite number of sine function, it could be cos function also. It is known as Fourier series. Basically, a Fourier series changes a periodic function, what we have discussed in previous 2 slides about periodic functions. So this Fourier series, it changes a periodic function into an infinite expansion of a function in terms of sine and cos. Here an example. This figure shows a graph of the function y equal to 2 sine t. Again, this is only one function, sine t, 2 sine t. Amplitude is 2. If I bring another curve, this one, it shows a graph of 2 sine t minus sine 2t. The difference between these two figure, if we look at, already we have seen it was previous one was only this, but this one having 2 sine function. So we have included this second sine function. It has the twice the frequency of the first. Now go for the third one. 3 sine curves, equations, this. Three sine functions. See the shape of the curve, it is changing. Sawtooth. Again another. Four sine function. You look at the sawtooth, it is increasing and becoming small. This tooth, it is increasing and becoming more in numbers. Here, decreasing amplitudes but increasing frequencies. It is most important point. Decreasing amplitude, increasing frequencies. As more and more sine terms are included in the graphs, then it appears to be, we'll see it in the next slide, how it will appear. But here I have brought four in a same slide to get the comparison. Here, this one I have showed you first. This was second, 2 sine curve. This was 3 sine terms. Here, this is 4. See the changes of the sawtooth. So what it indicates? Here there is no sawtooth like. Here it is showing some. Here it is 2. Here it is more and small size. So if it would go more sine terms, I mean sine functions, so at an end this will be looking straight line. That is why I've said, as more and more sine terms are included, the graph appears to resemble more and more closely the periodic sawtooth waveform. So by using an infinite series of sine function, we can show that the sawtooth waveform can be drawn in a graph. That is why I've written here infinite series of sine function is the Fourier series of the sawtooth waveform. It's very important points, because in the next slide we'll do one examples, and in that example our this waveform should be like this one. So for a function fx, assuming it as periodic with fundamental period t, and this periodic function can be expanded in a Fourier series. That's what we are doing here. As I said in previous slide, this function Fourier series, it will be a combination of cos and sine. That's what it is. And here a0, a1, a2, a3 dot dot dot, again b1, b2, b3 up to bn are real constants. So this equation, it can be written as this also, because this is a0 by 2 as it is, and this up to this cos nx an, it can be written as summation n equal to 1 to infinity an cos nx plus from here to here b1 sin x to bn sin nx. We can write as summation of n equal to 1 to infinity bn sin nx, where for the range I have written here minus pi to pi, or it can be written as 0 to 2 pi. We can consider 0 to 2 pi also here. Now this is same equation, Fourier series. So what you will do here, our target is to find the value of a0 and to find the equation for an. So if we get the equation for an, then putting value n equal to 1, 2, 3, 4, then we get all a1, a2, a3 like this. Again, if we have equation for bn, we can find b1, b2, b3, putting the value of n equal to 1, 2, 3 like that. So what we will do, this is the basic equations for the Fourier series. So combination of sine and cos functions. So integrating both sides of equation from x equal to 0 to x equal to 2 pi. What you will get? We have to integrate both sides. Look at, in each term I put integration sign and limit is 0 to 2 pi. It is definite integral points, all the terms. Now if we do integration on each terms, then what we will see? Let's move. This will be 0. This term will be 0. This will be also 0. You can try, you can check it. It will be 0. I checked and that's why I'm putting 0. I'm not going to show you all the terms. This one also will be 0. This one also will be 0. This is also 0. Again 0. This is also 0. So look at what is the remaining, this one and this one. These two are the remaining. In the right hand side, this is left hand side. So let's take out these two. This equal to this. Now doing integrations, we get a0 by 2, 2 pi. Now this right hand side, this is left hand side. Transposing, we can get the value for a0. That's what it was our target, to find a0. Because we need to find a0, we have to find an as well bn. So we are done with a0, we got this. So let's see in the next slide how to find an and bn. Same equation I have written, Fourier series. So in this case, to find an, what I'll do? I will multiply each side by cos nx and integrate both sides, equation from 0 to x equal to 2 pi. So let's put the integration sign. Now, same way, lot of terms will be 0 if we do integrations. This one 0. This one will also be 0. This term will be 0. 0. So, remaining is this left hand side and this is right hand side, cos square nx. So we can bring these two terms out. And we get, integrating this term, I mean right hand side, we get this an pi. So easily transposing, we can write an equal to, this is the equations. So we got an. Now in next slide we will find bn. So let's move. Multiply each side by sine nx. Previous one we did by cos nx. This one we have to multiply by sine nx because we need to find Vn. So let's see which one comes or which will be cancelled for 0. This one 0. This will be also 0. This is 0. 0. 0. 0. So you saw now only remaining left hand side this and right hand side we have this only. So let's move to take out these two terms. So right hand side doing integrations we get bn pi. Transposing we can write the equation for bn. So we got the equation for bn. Now we found a0, an, bn. So let's see in the next slide all these terms. So I brought all these three terms, a0 equal to this, an equal to this, bn equal to this. And I have written here a0 and bn are called the Fourier coefficient of the series. Now it is very clear. If we want to find a1, a2, a3, we have to put the value for an, I mean an, n equal to 1, 2, 3, 4. Here n equal to 1, 2, 3, 4. We can find it. A0, an, bn. So let's see in the next slide. This is an example I have taken. As I told, if I get n1 equal to, n equal to 1, 2, 3, 4, we can find a1, a2, a3. If I put n equal to 1, 2, 3, again we can find, in equations for bn, we can find b1, b2, b3. So I have taken an example here. It is a function of x equal to x. So x less than 2 pi and 0, it is the same range what we have discussed in previous slides. And after getting the equations, we have to plot considering x equal to minus 4 pi to x equal to 4 pi. So let's move ahead to see how to solve this. So this is our Fourier series equation, combination of cos x and sin x. So let's see, with this function of fx equal to x, what you can do. As I told, we have to use this a0 equal to this. Already in the previous slide we got this. So this x, it is function of x. Now 2 pi 0, we have the range. So putting this limits, upper limit, lower limits, we get our value as 2 pi. So already it is very clear, a0 we got 2 pi. So we can put this a0 value here, 2 pi. Now let's move for finding an. Look at this, already this equation we have seen previous slide. We derived this. Now this function of x means x, and cos nx already it is there. So if we do integration, it comes as this form, and putting the upper limit and lower limit 2 pi and 0, and at an end we get this as this one. So once we get this, then we put this value 1 n square, this is pi, then this one is 1 minus 1 equal to 0. So this n equal to 0. Now let's move for finding bn. Same equation I put, only the thing we have to find using the bn equal to this equation and putting the value on all other things. I got minus 2 by n. So here it's very clear, putting n equal to 1, 2, 3, 4, because we got a0 equal to 2 pi, n equal to 0, bn equal to minus 2 by n. So very easy, if we put n equal to 2, 1, 2, 3, whatever we put as n equal to 0, so of course a1, a2, a3, whatever value comes, all will be 0. But for this one, Putting the value of n equal to 1, we get minus 2. Putting the value of n equal to t, we get minus 1. So b2 minus 1. Putting the value of 3, we get b3 equal to minus 2 by 3. This way we can get b4, b5, b6, whatever we want. Now if we put this value here, a1, a2, a3 all are 0, so all will be cancelled, only remaining this. So our equation takes the form as this one at an end. This is the equations we have. Now using this equation, we will plot. But to be sure with, here one sine term, there is another sine term, another sine function, there is another sine function, there will be another sine function up to n. So there will be lot of sine functions here. Sine term 1, 2, 3, 4, maybe 100, maybe 200 terms will be here. We don't know. But we have to use some of the terms to see what is the shape of the graph. So let's see in the next slide. Look at this equation. I have taken only 3 terms. See, 2 by 3 sine x. So sawtooth like that. If I take more terms, say here 3, I will take say 5 or 6 terms. Look at how many terms I have taken. Because pi minus 2 sine x, sine 2x, 2/3 sine, then I have taken, this is 4th one, 5th one, 6th one. You see the tooth, sawtooth? More sawtooths. If I take more and more sine terms here, so my this sawtooth will be number, it will be more and more, but this, I mean, dropping shape will be very small, but number will be more. But if more and more than 100 terms, 200 terms, then this will become a straight line. That is the interesting things for the Fourier series in sine function, in sine cos functions. So let's see what it would be if you take lot of sine terms in this equation instead of 6. Suppose instead 6, if I take 100, suppose I am not taking it, it's very hard to do, but assuming I have taken lots, so the shape will be straight line like this. So this is our graph, -4 to +4. If infinite number of sine functions are taken, here only 4, I have taken 6 also. If infinite number, then this will be a straight like this line. So you can compare. This is only 3 terms, this is 6 terms, this is multiples. We are assuming I have taken lots. So graph will be like this. That's all for today. And thanks for watching.